Thank you for attending this talk on classifying cardiac abnormalities in 12-lead ECG using wide and deep transformer neural networks. My name is Jonathan Rubin. I'm a senior scientist at Philips Research North America. And I just want to remind people that I am available to answer questions during the talk, so please do put your questions in the chat box. This is work that I did with some colleagues at Philips as part of the 2020 PhysioNet Challenge. And just before getting started, I want to just acknowledge the team that was made up of Malai Natarajan, Yael Chung, Sarah Mariani, Asif Raman, Greg Boverman, Shruti Vij, and myself. So just to orient the talk, I'm going to begin by giving a brief introduction, and then I'll describe the 2020 PhysioNet Challenge and describe the data set that we had to work with. And then I'll detail the approach that we came up with, which was a wide and deep transformer neural network architecture. And this approach ended up winning the challenge in 2020, and I'll present the results of the challenge. I just want to say a little bit about the work that we do at Philips Research just before we get started. So Philips is a healthcare company. And as such, they develop various sorts of medical devices, including ultrasound scanners, CT and MRI machines, bedside monitors that monitor patients' vital signs. And then Philips also has an increasing presence in image-guided therapy solutions. And our job as researchers is to take the data that is generated by these devices and work with it to create clinical decision support systems. And that data comes in many different varieties. So it could be clinical data, such as from electronic medical records. So time series data, but time series that's irregularly sampled. Or it could be, as in this talk, physiological waveforms. So this is much higher fidelity data. And then we also deal with medical imaging data, either 2D, 3D, or even 4D medical imaging data. But today I'm going to focus on physiological waveforms. And in particular, I'm going to talk about the 12-lead ECG. So doing automated analysis on 12-lead ECG to determine what cardiac abnormalities may exist within a particular recording is an age-old problem. This has been done for many decades. And there are good reasons for doing so. If we can create high-performing algorithms, then we can assist clinicians to diagnose the growing number of ECGs that are being recorded these days. What the 2020 PhysioNet Challenge allowed was an opportunity to assess modern algorithms on a very large data set that came from a wide set of sources. So if you're not familiar with PhysioNet, it is an online resource related to processing healthcare data and developing algorithms that process either physiological signals or various other forms of healthcare data. There have been a variety of challenges run in the last 20 years, including in 2019 a challenge on the early prediction of sepsis from clinical data. There have been challenges on sleep data, and then there have been a bunch of previous challenges also working with the electrocardiogram. Last year, the challenge was about specifically working with the 12-lead ECG. And I'm sure everyone is familiar with the electrocardiogram. Nowadays, you can record your ECG directly on a watch. There are various handheld devices, such as the AliveCore device, that can record a short ECG recording. And then there are patches, such as from iRhythm, that record 24-hour ECG, where you wear a patch on your chest. The data that I'm talking about today looks more like these two images here. So a 12-lead ECG would happen in a clinical setting. As a patient, you would typically be sitting up or laying down, and then you would have a bunch of electrodes placed on your chest as well as on your limbs, and then a recording would be taken. And I just want to talk a little bit about cardiac function and how the electrical activity of the heart shows up in an ECG recording. So here we have a normal heart. The electrical activity begins at the SA node, and then it emanates downwards throughout the heart. So a heart is made up of 4 chambers. You have the atria at the top, and then the ventricles on the bottom. And blood is going to flow from the atria into the ventricles. And when the electrical activity is organized, then this allows the heart to beat appropriately and for the blood to be pushed out through the aorta to service our vital organs. However, I've chosen one particular cardiac abnormality, in particular atrial fibrillation. And so what happens with this abnormality is that the electrical activity becomes disorganized. Instead of emanating only from the SA node, in atrial fibrillation, there are many points now where electrical activity is emanating from in the atria. And this results in this disorganized electrical pattern. And this is not good because now the heart, the atria in particular, begin to quiver about, and this can allow these blood clots to form. And if a blood clot breaks off and travels through the circulatory system, and then that clot gets lodged in a blood vessel, such as a vessel that services the heart or the brain, this results in heart attacks and this results in strokes. And so this is not good news. And we can look at the ECG recording to get an idea about whether this recording is normal or abnormal. In a normal rhythm, the ECG is made up of various waves. Typically, you'll see a P wave, followed by a QRS complex, and then later on a T wave. So these peaks here, these are what are known as the QRS complexes. And in a normal heart, we can see that the interval between these peaks, between the QRS complexes, is pretty regular. But if we go ahead and look at the recording for the atrial fibrillation heart, now we can notice that the interval between these peaks looks a little bit irregular. There are wider gaps or gaps that are not as long as compared to the normal rhythm. And this is a telltale sign of atrial fibrillation showing up in a particular ECG recording. One other finding that we can look for is typically in a normal rhythm, you would see a P wave just before this larger QRS peak. And we can see these P waves showing up in this normal rhythm here. But in the atrial fibrillation signal, we can see that the P waves are absent. Before the QRS complex, we don't actually see any P wave. And so this is another thing to look for, in particular for atrial fibrillation. And the 12-lead ECG gives us multiple ways of looking at a heart. This is what an exam might look like after a 12-lead ECG has been performed. And it's made up of the various limb leads and then the 6 chest leads. So each one of these recordings gives a particular view into the electrical functioning of a patient's heart. And we can see that the signals look a little bit different in each one. Sometimes the QRS complexes are facing upwards, sometimes they're facing downwards, and sometimes they're larger than in some recordings versus others. And so we were given access to the 12-lead ECG signal data as part of the 2020 challenge, as well as a very small amount of demographic information, including a patient's age and sex. The dataset that was released was the largest open access database of 12-lead ECGs, and it was drawn from 3 continents, and it was made up of a diverse and distinctly different populations. In total, there were roughly 66,000 recordings sourced from 4 different countries. And just over 43,000 of them were annotated and made publicly available for challengers to train and validate their algorithms on. The remaining 23,304 recordings were then not released. They were held back as hidden test data to evaluate submissions on. And then it was ensured that there was no patient overlap between the training and the testing datasets. So this slide shows the diagnoses that made up the labels of the 2020 dataset. In particular, there were 111 diagnoses that existed in the label space. However, not all of these labels were used to evaluate challenge entries. In particular, only 27 are used in the final evaluation. And these classes consist of things like normal sinus rhythm, so this would be the normal class. Then there is atrial fibrillation, as I mentioned previously. Atrial flutter is another type of abnormality that is somewhat related to atrial fibrillation. And then other classes such as bradycardia. This effectively just means a slow heart rate, as well as tachycardia, which is a fast heart rate. And then other types of arrhythmias. In total, the training dataset came from 4 different hospital settings. There was a dataset from China, from Russia, from Germany, as well as one from Atlanta in the United States. And these datasets varied by the number of patients and recordings, as well as the duration of the signals. So in the first dataset, signals ranged from anywhere from 6 seconds to 60 seconds. In the dataset from Russia, the recordings were made for 30 minutes, so these were much longer recordings. And then for the last 2, each recording was 10 seconds. They also varied by their sampling rate. So some were sampled at 500 Hertz and others at 257 Hertz. The testing dataset came from 3 different sources. 2 were extensions of the training dataset sources. And then there was a 3rd dataset that came from an undisclosed location in the United States. And so if you're familiar with other sorts of machine learning challenges like Kaggle, these typically last for approximately 3 months. The PhysioNet challenge is a little bit more involved. It lasts for the better part of the year, typically beginning in late January or early February. And there's an initial unofficial phase that goes to roughly the beginning or the end of April. So this allows time for challengers to get into the problem and work out any bugs that may exist. There's typically some things to sort out in the unofficial phase. And then things are set in stone, and then the official phase begins, where challengers have up to 10 submissions that they can make to the challenge server. And each of these submissions is going to be evaluated on a very small portion of the held out test data set. So there's a leaderboard and you can see how well your entries are doing. However, only at the end of the challenge, once the official phase has wrapped up, will the data be run on all of the held out test data, and then a winner will be announced. So at the 2020 challenge, there were 217 teams. They made 1,395 entries. However, only 703 of these entries were successful. So it's a little bit involved to make a successful entry. You have to Dockerize your entry. You have to pull together all the libraries that you're going to be using to train your model and to run your model. And in fact, last year was the first time that there was a new constraint that you also had to train your model on the challenge server. And there are various computational constraints as well in training and running your models. In particular, there is a 72-hour time limit to train each model, and then a 24-hour time limit to run the model as well. So now I'm going to get into more of the technical details about our approach. where we used a wide and deep transformer neural network. So this terminology, wide and deep, comes from a paper from Google in 2016, where the term wide refers to static features. These are traditional handcrafted features. We use traditional ECG signal processing features that we compute, and then we combine those features with a deep neural network. And the deep neural network processes the raw ECG signal itself. So in the next few slides, I want to discuss a little bit about the pre-processing that we do to the ECG signal. Then I'm going to go into detail about this wide and deep neural network architecture. And I'll talk a little bit about some of the implementation details and the design decisions that we made. So to pre-process the signals, we first resampled every signal to 500 Hertz. This is because the sampling rate differed based on where the data came from. Then we applied a bandpass filter ranging between 3 and 45 Hertz, and these values have been defined as appropriate for the cardiac abnormalities that we're interested in detecting. We also do normalize each of the recordings as well. So for every channel, we normalize a signal to be in the range of -1 to 1. And then for the deep portion of the network, we use a window approach. So we take 15-second windows of ECG data. And if it happens that the recording did not have 15 seconds worth of data available, then we would zero pad the remainder of the segment. So starting with the wide features, we first extracted roughly 300 traditional ECG signal processing features from the lead 2 signal. And these features capture information about heart rate variability, including time-based features as well as features in the frequency domain, and then also features based on nonlinear time series analysis. As well as features that are based on a morphological analysis of the signal. They look at the shape of the various intervals and the various waves that make up the ECG recording. And the first thing we did was we trained a random forest model, and we did this to investigate feature importance. So we selected the top 20 most features just by eyeballing the data. This was the plot that we came up with, and I know you can't see the x-axis clearly on this slide, but on the next slide I will list each of these features so you can see in detail what they were. What we noticed was that the first feature, the top most important feature according to the random forest model, was the waveform duration. And we decided to take that feature out because this effectively just tells the network how long this recording is. And we don't want our models to pick up on information about simply how long each recording is. This could allow the network to overfit to the data set, where it could learn these correlations that may not exist. So we excluded this feature, and then we took the remaining 20 most important features, and we also added the age and gender demographic information to that set. Here are the top 20 features that were identified by the random forest model, and we can see that they pick up information about heart rate. So in particular, the top feature was the minimum heart rate. We also had the maximum heart rate and the average heart rate in the top 10 features. The other types of features were RR intervals. So remember I mentioned about the distance between the QRS complexes, the peaks in this recording. That is known or referred to as the RR interval. And these features look at various information about how variable that RR interval is. And then finally, the other sort of types of features that were picked up on were entropy features about the various peaks and waves in the signal. So that was the wide features. The deep neural network component is made up of 3 sections. So now we're on sort of the left-hand side of this diagram here, where we're going to be processing the raw ECG data directly. And the first thing we do is we pass that to a convolutional neural network, so a series of convolutions, which we call the embedding network. So these convolutions are going to extract information directly from the raw ECG waveform. And remember, we're dealing with these 15-second segments. Once that's done, we're going to take those embeddings and we pass them to a transformer model. And this transformer is typically, these are encoder-decoder type networks. They're used in natural language processing as an alternative to recurrent neural networks. However, we're only interested in classification. So we only use an encoder and we don't need a decoder. And then the final part of the deep component is the multi-label classification head. So in particular, we want to predict 27 classes, and we want to make a prediction about every one of those 27 classes, whether it is present or absent in the recording. So I'll go into a bit of detail about each of these components. Starting off with the embedding network. Here we take the 12-channel ECG recording and we feed it through a sequence of one-dimensional convolutions. And we use quite large kernel sizes. We do a roughly 20x downsampling of that raw signal, and what we end up with are a series of vectors, and these are embedding vectors that capture some semantically meaningful information that's been extracted from the raw ECG signal. So we chose a dimension size of 256, so each of these vectors has a size of 256, and then we have a vector for each time point moving forward in time. So then we take the embedding that was learned and we pass it to a transformer neural network architecture. Transformers have become very popular recently. I'm sure people are familiar with them. They've had tremendous success in natural language processing, and nowadays are also being applied to computer vision tasks such as object detection as well as image classification. And particularly with regard to sequence type tasks, they have a lot of benefits. So they can be faster to train compared to recurrent neural networks. And this is because we no longer need to do things in sequence. Instead, things can be parallelized out. I'm not going to go into the exact details of how transformers work. Instead, I will point people towards the Attention is All You Need paper. And then there are also various blog posts online that do a very good job of explaining exactly how transformers work. I just want to give a very high-level conceptual overview of the basic idea, in particular around scaled dot product attention. And so I'll do that using this example, where we have some small input sentence, and we have words that are given to a transformer model. But we don't need to give these inputs, these words, in order. Instead, we can give all the words at once to the model, and the goal is to produce an attenuation matrix. So this matrix is going to tell us how much attention should each of the words in the input sentence pay to all of the other words. So for example, if we take the first word, we can see that it should pay a large amount of attention to itself because it's the same word. And then if we look at the other words in the input sentence, we might want to pay more attention to this word dog because we're referring to the dog. And so we have a larger attention value for that particular word, and then smaller values for big and red. And so that's the basic idea, is that we want to come up with these attention values that tell us how much attention is each input token paying to all of the other tokens in the input sequence. This is done through this formula here, where we effectively use the inputs to the network to come up with a query, a key, and a value that are learned by the neural network architecture, and then the result is this Z matrix, which corresponds to these attention values. And then there are a few design decisions to be made about exactly what this network architecture looks like. So in particular, because we were dealing not with a sequence-to-sequence type problem where we're trying to decode some output sequence, instead all we want to do is classification, we only used an encoder stack, and we used 8 encoders. We also use multi-headed attention, and then for the other design decisions, I will point people to our computing and cardiology paper that has a few more details. What I will say is that we followed the original implementation quite closely, although we did make some decisions to reduce the number of parameters to fit within the computational constraints that we had for this particular problem. And then the final component of the deep module, the deep part of our network, is the multi-label head. So here we add 2 fully connected layers. So after we have processed the input, we've run it through the transformer encoder, we add our 2 fully connected layers, and we concatenate the wide features that we had computed with the output layer. So now we want to produce 27 output nodes, and in particular we're going to apply a sigmoid activation for each of these 27 outputs so that we end up with a value between 0 and 1. And given that this was a multi-class, multi-label problem, this is typically trained using a binary cross-entropy loss function. In total, our network is made up of roughly 13.5 million trainable parameters. Okay, so let's take a look at some of the results. So to evaluate our results locally, we perform a nested 10-fold cross-validation. We do a multi-label stratification on the data set. We split it into 10 folds. And then we train on 8 of those folds. We use 1 fold as our validation set, and then 1 fold as our test set. And we repeat this procedure 10 times to get 10 different results. Here I'm showing the results for the challenge metric. I'm not going to get into the details about exactly what this metric was. It was a custom metric that came up with by the challenge organizers, particularly for this challenge. However, you can think of this as a weighted accuracy type metric where the organizers came up with this weighting matrix that tries to reflect the clinical reality that some misdiagnoses are more harmful than others and some are less harmful. So this matrix would effectively get multiplied by the confusion matrix produced by the classifier. Just to orient you to these particular values, 1 would be a true oracle, 0 would be an inactive classifier that just always predicted that there was nothing wrong with the patient. And then these values can also go negative. And we can see some slight improvement when we go from a 10-second model to a 15-second model. Probably what's a little bit more familiar for people is the area under the receiver operator characteristic. And so here I'm also showing the AUC values, where we received an AUC of 0.901 for a 10-second model, and then an AUC of 0.922 for a 15-second model. So once we had trained up a model and we were happy with its performance locally, then we would make a submission to the challenge server and have it be run on just a small set of the held out test set. There's a challenge leaderboard and you can see how your entry is doing. So our team was PRNA. we only made one entry, and when we did so, we were not too encouraged. In particular, we were coming in at place 86. This shows the leaderboard with the person at the top of the leaderboard up here, and then it also actually extends out even further below the screen that I'm not showing. But this was our entry. So we didn't think that we were doing all that well. And it came as quite a surprise when we learned at the Computing and Cardiology conference that we had actually won this challenge. And we can get a better idea about why that is by looking at the breakdown between the different data sets that make up the test set. So this is our team here, and we can see that these are the challenge metric scores for each of the 3 different data sets in the test set. We can see that we didn't do as well on the first one. So the top team achieved a challenge metric of 0.892, whereas ours was 0.761. But if we look at how that team did on the second and the third data sets, we can see that they likely overfit to the first data set, and they did much worse on the second one and the third data set. Whereas our entry was able to do much better on this third data set that had many more patients in this particular data set. What's more, recall that I mentioned that we had training data from database 1 and database 2, but there was no data made publicly available for dataset 3. This was entirely held out. And so our algorithm was able to better generalize to this entirely held out data set compared to the other teams. And this is effectively what resulted in our top score of 0.533. I just want to briefly mention the second and third place finishers. So the second place finisher was a team named Between a Rock and a Heart Place. They had a challenge score of 0.52. This was a collaboration between some universities in China and the UK. They also used a deep learning based model. In particular, they used a ResNet model with squeeze and excitation module. And then the third place finisher was the Heartbeats team. They had a challenge score of 0.514. This was also a collaboration between Ping An Technology in China, I believe they're an insurance company, and the National University of Singapore. Once again, they used a squeeze and excitation ResNet model. However, they had also some handcrafted rules for bradycardia, and they used an external training database as well. This slide shows the breakdown of the AUC values per class. Here I've color-coded these, so blue shows an AUC over 90, black is between 80 and 90, and then red is a class that could use improvement with an AUC less than 80. We can see that for some of the classes, like low QRS voltages, premature beats, as well as things to do with T-wave inversion, here the classifier could use some improvement. And then the other thing I want to sort of point out is that in our validation data set, we were doing quite well. AUCs that are very close to 1 for some classes. However, those values dropped quite a bit when they were evaluated on the test set, and so this is another area where the model can be improved. So just to conclude, we presented a modern deep learning-based algorithm for 12-lead ECG analysis. We combined deep learning with traditional feature extraction. We were able to achieve strong performance for a range of cardiac abnormalities. In the future, there are a couple of areas that I'm particularly interested in investigating. So one is this idea of using extra domain level information that we have in our label space. Our labels actually come from an ontology. We have an ordering, a hierarchical ordering, so we can construct a tree in the label space, and we can use some domain information to inform our models. And so this is one area that I'd like to look at in the future. Also, the challenge is ongoing this year. This year, the 2021 challenge is about investigating how well these classifiers can do when we don't have 12 leads, but maybe we have fewer leads, such as 2 leads, 3 leads, or 6 lead ECG. So thank you very much for listening. Please check out some of the other sessions on deep learning and healthcare, and I hope you enjoy the rest of this year's GTC.